Okay, hello everybody. This is Brian again, and I'm going to take a crack at problem 18.2. So 18.2 says express the surface integral over a closed surface S as a volume integral over the enclosed volume V if the integrand of the surface integral is vector n dot the stress tensor dot vector V. So a tensor dot vector is a tensor, and so that's a tensor function, which is going to be helpful when we bring out equation 18.2, where it says a tensor function dot n ds is equal of a surface integral is equal to the volume integral of a gradient dot f times the dv. So anyway, what we can do is we can directly substitute sigma and v for f, and then it's just a plug and chug from there, where we get our volume integral is the gradient dot sigma dot v dv. Okay, part B is not as simple, and luckily there were other people graciously trailblazing ahead of us to solve it. I'm just going to reiterate what they said as best as I understand it. So we have epsilon RMS xm and sigma js times nj. So our surface integral is now epsilon RMS xm sigma ji. No, JS, sorry, times NJ. So what we're going to do now is we want to equate this to our tensor function f. We need this n outside because of our dot n up here. And then we can, once again, substitute f in the other side. And here I'm going to change nj to the partial with respect to xj. So now we have epsilon RMS xm sigma js times the partial derivative of x times 2 with partial derivative of v. Maybe that should be a hard, whatever. So anyway, we can simplify this further to what uh, delta sub j epsilon RMS xm sigma js dv. And I think this this equals that. And I'm not entirely sure. So if anybody wants to comment and tell me why, that'd be great. Alrighty. Thank you guys. Have a good one.